Hello everyone, you are here at Bohr-bury Educare and I am your host Dr. Tasadduk Wani. Today we are going to study the Hund's rule of maximum multiplicity. I hope that you guys have gone through other rules explained in different lectures of Bohr-bury Educare. If you have not, then go ahead and browse our channel for the Pauli's exclusion principle, for the Aufbau Principle and the Bohr-bury rule. You can find the links in the description. Now let's move forward towards today's lecture. The Hund's rule of maximum multiplicity came into being from the data that was observed from the spectra of atoms. Have you ever heard of the term multiplicity in quantum chemistry? Multiplicity in quantum chemistry means that a number is defined for any energy state. Mathematically, for any energy level or an orbital, the multiplicity can be defined as 2s plus 1, where s is the spin or total spin angular momentum. Also, the number of unpaired electrons plus 1 gives us the multiplicity. Since the unpaired electrons also give us an idea or information about the orientations or possible orientations, multiplicity is also equal to the number of possible orientations. This multiplicity is a number, and if it is 1, 2, 3, etc., then we can say that the energy state has a multiplicity of singlet, doublet or triplet. Now let's look at the statement of the Hund's rule of maximum multiplicity. This rule states that if degenerate orbitals or same energy orbitals are available, then the electrons will start occupying the orbitals singly with one spin until all orbitals contain electrons, and then afterwards start pairing in the same orbital. In simpler words, pairing of electrons in the orbitals of same subshell does not take place until each subshell is singly occupied by electron. Now, since we know s orbital has only one suborbital, while as the p has 3 suborbitals, d has 5 different suborbitals, while as the f has 7 different suborbitals. Therefore, the pairing of the electrons shall start only when the 4th, 6th and the 8th electron is available. That means in case of s, the pairing will start at first, while as in case of p, 1, 2, 3 electrons will go one by one first, and then only when the 4th electron comes, then the pairing will start. For d orbital, 1, 2, 3, 4 and 5 electrons will be filled first, and then only when the 6th electron comes, the pairing is going to start. Here the 4th electron comes, the pairing is going to start. D, the 6th electron comes and the pairing is going to start, and in this case only when the 8th electron is going to come, the pairing is going to start. In other words, I can say that for p, d and f orbitals, there are 3 suborbitals, 5 suborbitals, 7 suborbitals, and for single occupancy, that means when the electrons are filling all these orbitals in a single case, that means for p we have only 3 electrons, then these orbitals will be filled in the single orientation, while as here the 5 electrons will fill all of the orbitals in a single orientation, and in case of f, 7 electrons will fill. However, the pairing will start only when the 4th electron comes into the shell. Here when the 6th electron comes, and in case of f, when the 8th electron comes into the orbital. And a total of 6 electrons are needed here for full pairing, and here 10 electrons are needed for full pairing, and here 14 electrons are needed for full pairing. All of these orbitals that I have shown here, they are called as the degenerate orbitals. Degenerate orbitals means having the orbitals that have same energy. So in case of p, all the 3 suborbitals have same energy, for d all the 5 suborbitals have same energy, and for f all the 7 suborbitals have the same energy. Now let's consider some cases where we will distribute electrons in these degenerate orbitals. For simplicity, I have taken the p orbital, and p orbital has 3 suborbitals, px, py and pz, and if we try to add just 3 electrons in these 3p suborbitals, there are at least 20 different combinations that are possible. Out of 20 different combinations, I have shown 10 combinations here. And among these 10 combinations, you can see that this combination, that is where all the electrons are occupied singly, this has more exchange pairs of electrons and hence is more stable. It also means that the exchange energy represented by EE is maximum for this combination, that is 3e. However, on the other side, the pairing of electrons, when the fourth electron comes into the p orbital, it tends to destabilize the system or the orbitals. Hence, we always use exchange energy along with the pairing energy, represented by Pe. So when we combine exchange energy with the pairing energy, this kind of arrangement means that all other arrangements that are possible have less exchange energy, while as this combination has maximum exchange energy available for it. This suggests that this combination has more stability also, because it has maximum pairing energy and it has maximum exchange energy as well. Also, symmetry of electron charge distribution comes into play along with promotional energy in electronic configuration, which we will discuss in some other Bohr-bury lecture. This concludes our lecture. I hope that you guys enjoyed it. Also, your comments mean a lot to us. Please do subscribe for our latest videos and hit the like button. Until next topic, take good care of yourself.